Hi everyone. Today we'll start our tutorial 5. In tutorial 5, we will mostly discuss the topic that is a canonical ensemble that we have actually started in our last tutorial. So, in this tutorial, we will basically do a further discussion on the canonical ensemble subject. So, before starting it, let me rewind the things that we have learned in the last tutorial. So, so we started our topic of discussion. Uh, okay, revision. So we basically started our last discussion from the concept of the negative temperature. Okay, so we actually developed a like theoretical approach how this kind of negative temperature can be achieved and what will happen when a system is subject to a negative temperature, what happens to its states. Okay, so let's suppose there are two levels, n plus and n minus levels are there. uh, One has energy E, one has 0. So in this case, the distribution of the particles would be n plus by n minus would be n plus is the number of particles in each E state, first excited state, and n minus is the number of particles in ground state. So the ratio of n plus and n minus should be e to the power minus E by kt. E basically is the energy difference, E minus 0, that is basically E itself, right? So now if you do a little bit mathematics here, then you can write this temperature in terms of energy by K divided by ln of n minus n plus. Okay, now here we have discussed this so in this case, as you can see, this energy cannot be negative, it should be positive. This thing also should be positive, right? So the only thing that can be negative is this thing, right? So if these things become negative, then the temperature will also become negative, right? So if ln n minus or n plus become negative, then it implies that temperature will be also become negative, right? So when this whole thing will become negative, when n plus would greater than n minus, right? Like if you take log of the both side, like e to the power, if you take e to the power on both side, it will become n minus by n plus less than e to the power 0. So e to the power 0 is 1, so this will become n minus n plus. So n plus should be greater than n minus, right? This is the condition. So that means uh, in case of negative temperature, the number of particles in the first excited state should be higher than the ground states, right? So that is the condition under which the negative temperature is achieved. Okay, so now based upon that, we have done some mathematical problem where we have subjected a system of particles with a temperature path that is with a negative temperature, and we have find out that how the particles are basically distributed, like the fraction of particles distributed in higher energy state and the fraction of particles that are distributed in lower energy state. And we have found that indeed it is true that the particles that is in higher energy state, the number of particles is higher than the particles that is in the lower excited state. Okay, so also we have discussed this, the concept of negative temperature in case of a Carnot engine, right? Like the Carnot engine in general like extract heat from a hot source to a cold source, and during that it will do some work. But we have discussed what will happen if you, instead of a hot source, you just connected the Carnot engine with a source that has a negative temperature. Okay, so in that case we found out that basically the efficiency of the engine will become greater than 1. So that's the sort of a thing we have discussed about negative temperature. Also also we have calculated for a two level system, for a two level system we have calculated, first thing that we have calculated is the partition function, right? Then we have like shown how the behavior of the partition function will be in case of different ranges of temperature. Like if temperature tends to become much high, if the temperature tends to become 0, or it's become negative to a very high negative value. So in that case what will happen basically? So we have found out that the partition function shows this kind of behavior. Suppose this is kT. In this axis there is this temperature, we scale it by kT by epsilon, and this axis is partition function. This is a value 2. So we found out the partition function looks like this, and so this is 2, right? And this axis, this is 0. Okay, so it got something positive value here when it tends to, then it tends to infinite, tends to this 2 value. So yeah, it's like this. Okay, so we have basically found this value of t, like at t tends to 0 plus, tends to 0 minus, tends to infinite, plus infinite, and minus infinite. So all these four cases we have calculated the partition function, and we got this kind of a curve where you can see around 0 this curve is showing a discontinuity. Similarly we have also calculated the internal energy. At similar limiting value, t tends to 0 plus, approaching 0 from the positive axis, approaching 0 from the negative axis, plus infinite, and minus infinite. So all for the four cases we have calculated the internal energy. And for internal energy also we get sort of this sort of a curve where this axis it's kT by epsilon, this is 0.5, this is the internal energy U. So the curve qualitatively looks like this. Okay, Q gets a value here, here it's 1. here it tends to 0, and here it tends to 0.5. So okay, so like this is internal energy, this is kT by epsilon. Okay, so this kind of a thing we got. Lastly, we have can also shown how the entropy varies. Okay, entropy, but for the entropy we got something interesting. Okay, so here also it's discontinuous at 0, right? This is 0. Okay, this is 0. So this is also the internal energy. We have find out that there is a discontinuity close to 0. But for the entropy thing, we got it like this. Like similar way, like for the 4 limiting cases, we have calculated the entropy. But the entropy looks like this. This is basically 0, S, and this is kT by E. Okay. This is the, so this for entropy thing, as you can see, this entropy is continuous. The main thing is that the other two things, that partition function, internal, both are discontinuous, both have shown discontinuity around 0, but entropy remains continuous. Okay, these are the some things that we have discussed in the last. Next we have introduced the concept of the canonical ensemble. So in the canonical ensemble, so here we are considering that the particles are interacting. Okay, so so when the particles are interacting, so there are like, previously what we discussed is like this, like each particle, that is some energy states are there, and each particle got some like pre-allocated energy levels, like this, like the particles are basically distributed with a certain energy level. Okay, but but in the canonical ensemble, what we are basically doing, so in case of a canonical ensemble, the thing are a bit different. So here we have considered a collection of the systems. Okay, like the whole system in VT. Let's suppose the particle, like suppose it's a closed system, so that means the energy, the number of particles, the volume and temperature are fixed, but the energy can change. So for this kind of a system, we can create a collection of the system which are known as the, which the whole thing as a whole known as ensemble. And each of these members of the ensembles, these are the members, each have N, V, T. So each of the members are basically connected with itself. So that means they are like thermodynamically equilibrium state. So all of the members has a common temperature T. So these are the basically members of ensembles. Okay, now let's suppose there are n factorial, sorry, total number of members are equal to n tilde. Okay, and let's suppose total energy, the total energy of the whole ensemble, total energy of the ensemble is E tilde. In that case, uh, we have find out that the number of members in the ensemble having energy EI would be Ni tilde by N tilde, that is total number of members in the ensemble, equal to e to the power minus beta EI by capital Q. Capital Q is the canonical partition function, okay. And Ni tilde is basically there are like many members of the ensemble exist there. So we have find out like which of the members of the ensemble has the energy value EI, okay. So that is basically denoted by here as this Ni tilde, okay. So so now from that we have derived several quantities like how the internal energy. So internal energy expression will be looks like this: U equal to U0 minus delta of ln Q by delta beta at constant volume. Next we have derived the entropy. Entropy is U minus U0 by T plus K ln Q. Here Q is the canonical ensemble, okay. So so these are basically the certain things that we have done in our last tutorial. So now for today's tutorial we'll start something new. So not new, basically the extension of the previous discussion. So what we will do first, what we try to do, we want to write the Q, the canonical partition function in terms of small q, that is molecular partition function. That will be our first job to do, okay. So write the my canonical partition function capital Q in terms of molecular partition function Q, okay. So in order to do that, so what we do, we like as a collection of members which are known as ensembles, NVT, 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 like this. Each of the members has some energy E1, E2, E3, E4, okay. So each of the members basically denotes the possible states the system can achieve, okay. So let's suppose that at a particular state EI, at a state I state, let's suppose at a state I, the energy of that state I would be EI. That means the energy of that particular member, okay. So that energy EI will consist the energy, suppose capital EI, will consist the energy of each of the molecule, right? That energy of that particular the total energy of that particular member will be just like the addition of the energy of individual molecules, right? So let's suppose the molecule 1 at ith state has energy EI1, the molecule 2 at that energy state. Okay, so let me start. So So where we are? So the particle, so molecule 1 has energy EI, molecule 2 also, molecule 2, energy of the molecule 2 at the state I. Similarly, the energy of molecule 3 at the state I. So you have to sum it up all. Then from the expression you got, so then from there itself, uh, this is for ith state, right? Now from here you can calculate the canonical partition function Q. If you basically sum over all the possible states, 1, 2, 3, 4, here you are considered a general step I, but if you sum it up for the all possible i's, then from there you can easily calculate the total canonical partition function. Okay, so the expression will looks like this: e to the power minus beta ei1 ei2 ei3. So it basically comes from there, q equal to summation over I to the power minus beta ei. So from there you can write it like this. Okay, now here you can, what you can do, you can do this summation over individual molecules, right? You can write it like this: e to the power minus beta ei1, the summation of all possible states that can be happen to a particular, to the first molecule basically. And similarly this is multiplied by the second molecule, 2, third molecule, 3, ei3, so like that. Okay, now if we multiply the whole thing, if suppose the single, for a single molecule per partition function is this, ei would be this q, then you can write q as q to the power n. Okay, q is the single molecule partition function, the all, like all the energy state that that particle or that particular particle can basically achieve. So from that information you can calculate the single particle partition function, right? Function. So you have substitute that into this main equation here. So from that you are writing this whole canonical partition function in the terms of single molecule partition function. Now after this thing I've achieved, okay. So this is for distinguishable particles. Okay, like in this case, the particles are distinguishable and independent. Okay, so we can distinguish each of the particles from the other one, right? Now if you consider, so this is for distinguishable independent particle. Now if we consider let's suppose we consider for indistinguishable independent particles. So for indistinguishable particles, the form will be a bit different. In that case, the capital Q would be Q to the power n by n factorial. Okay, this is for indistinguishable particles. Okay, so this is how basically the canonical partition function, the canonical partition function, that is capital Q, is related to small q. So okay, so now what we will do, we will now calculate for both the case of distinguishable and indistinguishable particles, what would be the expression of the internal energy, and from there we will calculate the entropy, and we will from there we will do some problems also. So first will come the internal energy. Okay, so the general expression of the internal energy we have derived. Okay, so let's first consider the case for distinguishable particles. Okay, so for distinguishable particles, we will first use the general expression of the internal energy for a canonical system. So that would be looks like this, right? E equal to u0 minus 1 by capital Q del beta at constant volume. Okay, now you can further simplify it like this. Delta of ln Q by del beta at constant volume. So now, in this expression, as you know, for distinguishable particles, the capital Q can be written like this. Now, if you substitute this thing here, then it will looks like u minus u0 would be simply, if you do the derivative, so 1 by q to the power n into del beta of q to the power n whole at a constant volume. So u minus u0 would be simply minus 1 by q to the power n into q to the power n by q. 1q would become at the denominator, then del q del beta at constant volume. Okay, so now if you further simplified it, it will become, the minus would be there, n q and qn will be cancelled, n by q del beta at constant volume. Okay, so so this is the expression for distinguishable particle. Okay, where q is, capital Q is equal to small q to the power n, number of particles, right? So now the next case, for the next case, what we will do, we will extend this approach for indistinguishable particle and see whether the expression of the internal energy changes or what happens basically. So for indistinguishable particles, the q would be simply q to the power n by n factorial, right? Now, so u minus u0 is equal to minus n factorial q to the power n into del q to the power n by n factorial by del beta. Okay, now here you can do u minus u0 equal to n factorial q to the power n 1 by n factorial q to the power n minus 1 del q del beta at constant volume, right? Now here n factorial will cancel each other, so u minus u0 you will get as minus there is an n term also there, n. So minus n by q, there will be q also be there, 1 by q would be there, so del q del beta. So as you can see, we are getting the same result for the internal energy, where the particles are distinguishable or indistinguishable. Okay, and so the main theme is the internal energy basically remains unchanged. Okay, so this is the expression. Okay, now the next thing that we'll calculate is the so we'll consider this thing like for this case for the indistinguishable particles, and we'll look further into the entropy of the system. Okay, so And we will also calculate the entropy of a ideal monoatomic gas. Okay, the what will happen to the entropy first. But before that, first we will write the generalized expression for a distinguishable particle system. What is the expression of the entropy? So let me first write the expression of the entropy. So S is basically the entropy, which is U minus U0 by T plus K into ln Q. Right, this is the general expression of the entropy. Now here, what we will do, we will simply substitute there all these things. U minus U0 T plus K. Ln Q is nothing but Q to the power n by n factorial. Now you can just expand the things, U by U0, because you can write the ln in extended way, into ln Q minus K n ln n minus n. Right. Now from here you can write it like U minus U0 by T plus n K ln Q minus nk ln n minus plus nk. Now from here, so from here you can write, so this n is basically okay, so this n is basically number of moles in, n is basically the number of particles, right? So if for n if suppose there is n mole of particles is there, so that means the n would be n, that is the number of moles, into Na, that is the Avogadro number, right? So now we can write this nk, that means like this, n into Na into k, and you already know that Na into k is the R, which is the ideal gas constant, right? So you can write it like n into R, this expression, right? This is one simplification we can make. So this whole thing can be, we can write like this, is equal to U minus U0 by T plus nk ln Q minus nk ln n plus nr. Okay. Now from this, so so the next thing is, so we will have to also think about this term, right? This is the internal energy, right? This term we can also use some pre-derived results, right? We already know what is the internal energy of a ideal gas, right? Internal energy of the ideal gas is simply this, right? U minus U0, that also you have derived earlier, right? Equal to U0 equal to C by 2 nRT, right? So you just have to substitute this result here. So from that we will get U equal to 3 by 2 nRT by T, we have to divide the whole thing by T, plus nk ln Q minus nk ln n plus nr. Now from here we will do what we will do. S would be, the whole thing will be simplified, 3 by 2 nr. There will be another nr coming from the expression nk ln Q minus nr. So here also we can substitute this, all this nk's into nr, right? Nr ln Q minus, here also nr ln n. So S would be 5 by 2 nr plus nr into ln Q by n. Right, now from here what we'll do, we can write this whole thing like this, nr into ln of e to the power 5 by 2. So basically you can write this any number, let's suppose a number z x, you can write this x number like this, ln of e to the power x. This basically results to the number x. Okay, this just we are doing to make the equation in a closed form. Okay, ln into e to the power 5 by 2 into v is sorry, it's q, then it will become n. Okay, now, okay, so now this is the entropy expression. Now, for let's suppose for a molecule which is trapped like single particle translational partition function of a particle that is trapped in a 3D box like this infinite 3D box. Okay, uh, just like the in the case of ideal gas, right? You can consider each molecules of an ideal gas is like trapped inside a 3D box. Okay, for 3D system obviously. Then for that kind of a case, the translational partition function expression you already know, right? For a particle in a 3D finite well, a single molecular partition function that is the Q you already know is nothing but V by lambda cubed, right? V is the volume of that box, particular box of the container, the 3D container, and lambda is the thermal wavelength, right? Thermal wavelength. So the expression of the lambda was given by this equation 2 pi m whole to the power half. Okay. So there's a cube terms basically coming because we're considering the system a 3D system, right? So now if you substitute simply this 1D partition function, sorry 3D partition function, molecular partition function here, then the entropy expression would be looks like this. It would be simply nr ln of e to the power 5 by 2 into V by, you can write this n number of molecules like this, the way we have defined earlier, Na into V is there, V by lambda q. V is coming from, like we are substituting with q here. So this is the whole expression you are getting. Also, there are many ways you can write, right? So you can use PV equal to nRT, right? You already know this. So V by N is equal to RT by P, right? So if you substitute this here, then you can write this whole thing like this, NR into ln of e to the power 5 by 2 RT by P NA by lambda Q. So lambda Q. So it depends upon the condition of the problem that you're dealing with. So if suppose in the problem the pressure is changing, the volume remains constant, or if the volume is changing, pressure and temperature is remains constant. So in so in the different scenarios, you can use the like the different kind of expression of the entropy. Okay, depending upon the situation anyway. So this equation basically, whatever the kind of equation that you're using, whatever the form, pressure in terms of pressure or in terms of the volume, this equation basically known as the Sackur-Tetrode equation. Sackur-Tetrode equation. This equation is basically known as the Sackur-Tetrode equation. So this equation basically relates the entropy of an ideal monoatomic gas. Okay. So here we are deriving it for actually for ideal monoatomic gas, okay, which basically relates the entropy of that gas to the pressure, volume, as well as the temperature of the gas. Okay. This is a very basically useful equation. Okay. So using this equation, you can easily calculate the entropy of like entropy of any kind of systems. Okay. So let me just revise what we have done till now. So so we have like continued our discussion from the canonical ensemble, which is a collection of the systems, collection of systems which are basically in thermal equilibrium with each other. So, so from there, we are considering that each of these members of this ensemble has a different energy state E1, E2, E3. We consider that at a particular state EI, the energy of the state EI would be basically the summation of the energy of the each molecule in the system, right? So we have like write this whole energy in terms of the energy of the each constituent molecules of the system. That is associated with the energy state I, and from there we have first write the total canonical partition function, that is capital Q. The capital Q expression looks like this, right? Now we have somehow related that capital Q, the partition function, the canonical partition function, with the single molecular partition function small q. So this whole relation looks like this: the capital Q equal to small q to the power n. N is basically the number of particles, and this we have done. This relation we have proved is for distinguishable particles, distinguishable independent particles. Now let's suppose if the system becomes indistinguishable particles. In that case, the expression of the capital Q will become like this. So capital Q equal to small q to the power n. The whole thing will be divided by the n by a factor of n factorial. So so this is how the canonical partition is related with the single molecule partition function in both the cases, right? And the next we have discussed how the expression of the energy, internal energy. Okay, so internal energy we have derived, like we have just substitute the capital Q expression in the expression of the internal energy. From there we got both for the distinguishable and indistinguishable case, and the thing is, for the both the cases we got the exact same expression of the internal energy. Next what we have calculated is the entropy. So here the entropy entropy. So we started from the expression of the entropy from statistical mechanics, and there we are using this indistinguishable particles because we want to calculate the partition function of a monoatomic ideal gas. As you know, in case of a monoatomic ideal gas, all the gas particles are basically identical to each other. That means they are basically indistinguishable if they are identical. So we are using that. We are using simply the fact the particles are indistinguishable. So we are using the formula where capital Q equal to small q to the power n by n factorial. After substituting that here, we will do this algebra. We will change some of the parts of the equations. Then after doing all this algebra, we are getting this form, this kind of a form. But also we have substituted the expression of the single particle partition function, what we have actually derived in our last classes. So where the small q is like the v of the lambda. V is the like the container where the particle is trapped. Lambda is the thermal wavelength of the particle. And after doing all the substitution, these are the closed form of the equation of entropy. In terms of volume, you can write, or in terms of pressure and temperature also you can write. So whatever, this is known as the Sackur-Tetrode equation, okay, for an ideal monatomic gas. Okay. Now we'll do some problems. So the problem number 1 is it's we have been asked to calculate the standard molar entropy of gaseous helium at 25 degrees centigrade. Okay. So temperature is 25 degrees centigrade. Okay, so T is basically, so everything is standard. Okay, standard means that the pressure should be remain 1 bar, that is around 10 to the power 5 Pascal, right? The molar mass of an helium is mHe, the molar mass. Molar mass means the weight of 1 mole of helium, that is basically 4.002602 U. U is the atomic mass unit, okay. And temperature is 25 degrees centigrade. So T is equal to around 298 Kelvin. Okay. Now, given this condition, now we have to write out so now we will have to use, so pressure and temperature is given, so that means it will be useful for us to use this formula, okay, but the entropy is written in terms of the temperature and the pressure, okay. So now what we will do, we will use this. So first let me write the formula. S, so entropy S equal to R ln ln of e to the power 5 by 2 kT by P lambda q, where lambda is h by 2 by m kT. So here m is the mass, which is AU. So first let me write the mass in terms of kg. So mass would be 4.002602 into so if you substitute the expression, the atomic mass, so the weight of a proton, if you substitute here, so the mass would be simply changed into 6.6465 into 10 to the power minus 27 kg. Okay, this would be the mass of a helium atom. Okay, now next, other constant values. So R values you already know. R is 8.314 into 10 to, so sorry, 8.314 into joule per mole per Kelvin, right? Similarly, the Kb, the Boltzmann constant value is 1.38 into 10 to the power minus 23 joule per Kelvin, right? Similarly, the Planck's constant is also needed in order to calculate the thermal wavelength. The Planck constant value is 6.626 into 10 to the power minus 34 joules into seconds. Okay, so now first thing what we will do is calculate the thermal wavelength. Okay. After calculating the thermal wavelength, we will just simply substitute that thing into the expression of the entropy. Okay. So thermal wavelength expression is this, h by 2 pi m kT. So h is the Planck's process 626 into 10 to the power minus 34 by 2 pi into 6.6465 into 10 to the minus 27 into the Planck's constant, the mass. The mass is already written by K value, the Boltzmann constant 1.38 into 10 to the power minus 23 into 298, right? So now this is the lambda value. So lambda value we need to calculate. First let multiply 2 into pi into 6.646 into 10 to the power minus 27 into 1.38 into 10 to the power minus 23 into 298. Okay, multiply this whole thing divided by square root, to the power square root, and then we have taken divided this thing by 6.626 into 10 to the minus 34 and the final result I'm getting is around 5.05 into 10 to the power minus 11 meter, picometer order basically. So now once you got the expression of the thermal wavelength lambda, then next what you have to do, simply put the expression into the expression of the entropy. Okay. So the expression of the entropy, if you put it in the expression of the entropy, let me write Sm equal to R is the ideal gas constant. So R is nothing but 8.314 into ln of e to the power 5 by 2 e to the power 5 by 2 into kT. K is 1.38 into 10 to the minus 23. K is the Planck's Boltzmann constant. Yeah, temperature is 298. What is this P? P is in Pascal, right? It's standard pressure temperature. So P is 10 to the power 5 Pascal, and the thermal wavelength is 5.05 into 10 to the minus 11 whole to the power 2, right? Now if you simply calculate this, let me do the calculation. So inside the ln, we have to write e to the power 5 by 2 into 1.38 into 10 to the minus 23 into 298, the whole thing divided by 10 to the power 5 into 5.05 into 10 to the power minus 11 whole cube. Okay. Now if you take the ln of this, will gives you this. Okay, then you have to multiply it to 8.314, which gives you, okay, so Sm you got 126.2 joule mole inverse Kelvin inverse. Okay, so this is the entropy you are getting. Okay, now we will do a similar type another problem with different molecular mass. Okay, for xenon, let's suppose now we want to calculate the same thing, standard molecular entropy of gaseous xenon. Okay, xenon at 25 degrees centigrade. Okay. Now at 25 degrees centigrade, so what, first thing, the temperature will now become 298 Kelvin. Pressure will become 1 bar. 1 bar means 10 to the power 5 Pascal. The xenon mass, the mass of xenon is atomic mass 131.293 U. So now the similar way, what we will do, first we have to calculate the thermal wavelength. So the thermal wavelength expression is given by lambda is simply this h by 2 pi m kt. Now here lambda is h, you know, 6.626 into 10 to the minus 34 divided by 2 into pi into m. Mass is simply, if you multiply this into u, by the way, u's value is this. The weight of a proton, 1.66 into 10 to the minus 27 kg. So this will give you the mass of an xenon, molar mass, particle mass, or whatever, 6.6465 into 10 to the minus 27 kg. This will be the mass of xenon, right? Now that's if you got this, now 2 pi into, just substitute this, 6.6465 into 10 to the power minus 27 into the so 2 pi m we got. Now k value is 1.38 into 10 to the power minus 23 into 298. Now if you calculate all of this, sorry, it's the mass is so it's not this, it will be 2.179 into 10 to the minus 25. 2.179 into 10 to the minus 25. Okay, so now the lambda value we got there. So if you calculate this, you will get the lambda as 8.82 into 10 to the power minus 12 meter, again in picometer unit. So now the entropy is simply just substitute all of these things, entropy expression are 8.314 into ln of e to the power 5 by 2 is there into the, what is there, entropy expression kT, right? K has a value of Boltzmann constant 1.38 into 10 to the power minus 23. T is 298 here. Pressure, the pressure is in the denominator, right? Yeah, P by lambda into lambda cube. So pressure is 10 to the power 5 into lambda cube is 8.82 into 10 to the power minus 12 cube. Okay, so this is the expression of the entropy I'm getting. So entropy is 169.7 joule into mole inverse into Kelvin inverse. This is the expression of the entropy I'm getting, right? So yeah, so okay, so let's, depending upon the problem, so one inference that you can draw immediately from the problem is, as you can see, for higher molar mass, like for the case of a helium, the molar mass was smaller compared to the xenon case, right? So here you can see the entropy is also smaller. So if you increase the molar mass, the entropy also increase, like in the both the cases, right? Let's see. So so this is the one thing, one inferences that you can conclude. Next thing, okay. The reason is because the lambda is inversely proportional to the molar mass, and the entropy is also inversely related with the lambda, right? So in that case, the entropy would be proportional to the molar mass, right? So sorry, the mass of the particle, right? So for that reason, if you increase the mass of the particles, or the molar mass of the particles, the entropy will also definitely get increased, right? So anyway, so how we are basically calculating, so depending upon the problem, so first thing what you have to find out that what are the variables that are supplied, the pressure, mass, the temperature. Here the problem is mentioned standard, so you can use the standard atmospheric pressure, that is 1 bar, that is equal to 10 to the power 5 Pascal. Then the mass of a helium that is supplied in the problem, that is 4.002602 atomic mass unit. Temperature is 25 degrees centigrade Kelvin. So now here from the description of the problem, the pressure and the temperature is given, supplied. Okay, so you have to use this formula, the second formula of this Sackur tetrode equation. So so in that expression, if you just substitute the values, there's a lot of constants are involved in the equation. So you have to first substitute the constants there. The next you have to substitute the lambda, right? The lambda thermal wavelength. So first what we have done, so we like in a separate way we have calculated the value of lambda, and that value of lambda we substituted here. So after doing all the substitution, you are getting the entropy value like this. Okay. So this is the one of the way you can calculate entropy for a particular case where temperature and pressure is given. So next we will calculate. We will check how this change in entropy. So we will check the how this change in entropy that we have derived from the statistical mechanics, whether it is consistent with the expression of the entropy, change in entropy that is already there in case of a thermodynamics. What like the change in entropy that is basically derived from the thermodynamics, whether it is consistent with the change in entropy that is derived from the statistical mechanics. So we'll check the consistency of entropy for thermodynamics and the case of statistical mechanics. Okay. So how we'll start? So we will first, let me first write the expression. So we'll start. So for our easiness, we are writing the expression of the entropy in terms of volume. Okay. Integral 5 by 2 V by A into NA lambda Q. So here the expression of the lambda is basically given into the beta h square 2 by n to the power half, right? Or you can write it like this also, yes, 2 by n kt, or whatever format you prefer to be written, you can write in that format. Now there are a lot of constants involved, right? So you can combine all those constants together and write it in terms of just a single constant, right? So S would be then nr into ln. I'm combining all of this constant into a one simple constant value, that is the A. So nr will be ln into AV. Okay. But A is the constant here. Okay. A is the constant. Right. So now, so S is basically nr into ln AV. Now, if you change the volume, so if you change the volume, so here the entropy is dependent on the volume, right? So entropy will only change if you change the volume, right? So let's suppose the system basically initially was in the volume Vi, then at later time system evolved into a volume VF. Then in that case, what would be the change in the entropy? That is pretty straightforward, right? So delta S would be simply nr into ln A into V final minus nr into ln A of V initial, right? So delta S would be nr. So you can write this subtraction of the log as division inside the log, right? So it would be, so the constant term inside the log would be cancelled, right? So VF by VI. Okay, so this is the change in entropy when you change the volume. So this results we got from the statistical point of view. Okay, right. Now next in the case of classical thermodynamics perspective, we know ds the entropy is related with the change in heat for a reversible process. The change in entropy is related with the heat by this formula, right? ds equal to dq reversible by temperature, right? So now from here what you can do, du is dq plus dw, right? So dq equal to, now uh, for isothermal, let's consider isothermal case. So isothermal means du would be equal to 0, so dq would be minus dw, right? So dq would be, dw is nothing but pdv. So pdv is there. Now p, you can write pv equal to nRT. So dq would be minus nRT by v into dv. Now dq you can write it as TdS, that is coming from here basically, TdS. Now it's equal to nRT minus nRT by v into dv. dt will cancel, so ds would be simply minus nr dv by v. Now if you do the integration both sides, ds from s initial to s final would be equal to minus nr, the integration would be going from v initial to v final on the volume expression. Then this is SAF by SI, that is the delta S would be equal to minus nr ln of Vf by Vi, right? So delta S is basically, okay, so okay, so there is a minus sign there, right? So yeah, so here there will be a minus sign will be there, so minus minus so minus minus will get plus, you know, plus there's a minus will be there, minus pdv, right? So minus minus will become plus, and this term will plus, so delta should be nr ln vf by vi, right? So as you can see, both the results for statistics, statistical mechanics, and thermodynamics are pretty consistent with each other. So this means that, so what basically happens here? Okay. Basically, this means that if you increase the volume of the volume of the system, okay. So let me give you an example. So let's suppose in a container, the particular volume Vi, there is certain energy states are there, right? So each state, let's suppose it's a 1D kind of a container. So energy states, each energy levels are like this: n square h square by 8n l square. L is basically the length of this thing. Okay, like now if you make the container bigger, if you make the L bigger, then the energy levels, the like the difference between the energy levels becomes smaller. Okay, so that means more and more energy levels will be coming to the system. Okay, so if we expanded the whole thing, the En would become smaller, so that means the more and more energy levels, the energy levels are much more finer. So will become much more finer like this. If we increase the L to Vf, okay. So Vi, this is Vf. Okay. So as a result of this, there are more accessible states will be there for a particle, right? This this is the basically the physical reason why increasing the volume basically make more available states for a particle, which results into the increase in the entropy of the system. Okay. So this is the one thing. This is one thing. One result basically that you got from here. So now we will discuss some of the problems, okay, like on this particular topic. So the first problem is on isobaric expansion. So isobaric expansion is, let's suppose a system of 1 mole at a constant pressure, increase volume, increase its volume from V from 5 ml to 20 ml. Then calculate the change in entropy. Okay. So you have to calculate basically the change in entropy when the system of 1 mole at a constant pressure increases its volume from 5 ml to 10 ml. Then the change in entropy. So for that, constant pressure, right? So we can write this change in entropy, but the volume is for pressure is changing, and like the expression of the change in entropy in terms of volume we have to write. So Vi, so N is the 1 mole here, P is constant, V initial is 5 liter and V final is 20 liter. Now for monoatomic, so the system is basically monoatomic, not diatomic or something like this. Monoatomic ideal gas at constant E. Change in entropy delta S would be simply NR. So R would be, so NR is like so NR is NR into ln NR into ln VF by VI, that is NR into ln 20 by 5, that means NR into ln 4, and if you multiply all of this, N is 1, R is 8.314, and M is 1.3863. If you calculate this, 8.314 into 1.3863, 11.534. I'm getting 11.52 Joule per Kelvin per minute. Similarly, for compression, let's suppose for isobaric compression, here similar monoatomic ideal gas compressed from volume 120 liters to 30 liter, and N is 1 mole at constant pressure. Now for this case, similar way, the change in entropy delta S would be here the VF is 30 liter and VI is 120 liter, so it's compressed, right? Similar way, delta S would be NR ln of VF by VI. So similar way, NR is 1 into 8.314 ln into VF here is 30 by 120, so 8.314 into ln of 0.25. This gives you, so whatever you got in the first case, you will be getting the negative of that result. That would be 11.52 minus 11.52 joule per Kelvin inverse millimeter. So this is what happens when you basically expand the gas, the states are increasing, which results into the increase in the entropy. But when you decrease the systems, decrease the volume of the system, the energy, the possible states numbers are also getting decreased, and as a result, the entropy of the system is also getting decreased, right? So these are basically the various cases we have discussed so far. So now from here, now from here, we will consider the case where we are instead of changing the volume, if we take a condition where instead of changing the volume, we will be changing the temperature. Okay, so find delta S from change in temperature at constant P pressure, right? So let's suppose the molecule here is n equal to 2, let's suppose 2 mole is there. Pressure changes from, temperature changes from, changes from 300 to 600 Kelvin, right? So for that case, the delta S expression is now we have to write in terms of temperature, right? Previously it was NR into ln VF by VI. Now for ideal monoatomic gas, you know, PV equal to nRT. So V is directly proportional to T. So now we can write delta S as NR into ln TF by TI. So in that case the delta should be nr ln tf is 600 Kelvin by tf is 600, ti is 300. So this gives us nr into ln2. So ln2 you already know 0.693, something like that. So yeah, so r is 8.314 and 0.693. This basically gives you I think, let me calculate. Mine is in the calculator. 8.314 into, so 8.314 into 0.693, this gives you 5.76. Okay, so 5.76 joule per Kelvin. This is the delta. Okay. Here this equal to 2. Okay, this should be multiplied with 2 then. So 2 and mole was 2, right? So 11.52. Now it's fine. Yeah. So this is the entropy. Like if you change the temperature, also its entropy will change. In this case, you like have to just write the change in entropy in terms of temperature, right? Next, okay. Now we consider the system consists of two independent subsystems with multiplicity W1 equal to 3 into 10 to the power 18 and W2 with 5 into 10 to the power 21. So that means the number of the weightage, W multiplicity means the weightage. That means the we have described it earlier, right? Like if there are suppose uh, n number of systems are there, right? In one, like let's suppose 1, 2, 3, 4. First, in the first state is in one number of systems can be there in state E1, E2, E3, E4. Into number of system in E2, M3 number of system in E3. So like that, if the system is distributed, that a whole n number of system is distributed like this, in that case, the possible configuration that we have termed it as weightage is this, right? In fact, factorial by n1 factorial into factorial like this, and n factorial like this, right? So this thing we have like previously derived, right? And you also derived that this weightage is somehow related to the entropy of the system. The more weightage the system has, that means the more entropy the system also has, right? So AS is basically the weightage is basically related with the entropy using this formula AB ln W. W is basically this weightage. Now in this problem, actually this two independent system, this weightage is given. Okay, this multiplicity is nothing but the weightage. Okay, so weightage is given 3 into 10 to the power 18 in the first case, second case 5 into 10 to the 21. Now the things that you have calculated, you have to calculate A, what is the multiplicity W of the combined system. The B is compute the entropies S1, S2 and total entropy S, and the third thing is comment on the result. Comment on the result. That means basically have to interpret the results, right? So the first thing is we have to calculate what is the multiplicity W of the combined system. So the first system has got the multiplicity or the configuration W1 as 3 into 10 to the power 18, and the second system has multiplicity W2 as 5 into 10 to the power 21. So for the combined case, since the systems are independent system, okay, since for independent subsystems, the multiplicity multiplies. Okay, basically the W is basically the of the whole system multiplicity. W is basically the multiplication of subsystem W1 and W2, provided the fact that both the subsystems are independent with each other, right? So the combined system multiplicity W is 3 into 10 to the power 18 into 5 into 10 to the power 21. That gives basically the whole multiplicity 1.5 into 10 to the power 40. The W voltage on the multiplicity, whatever things you want to state. So this is the multiplicity. We'll go it. Okay. Now the next thing, it has been asked to calculate the entropy, right? So entropy. So for the first you have to calculate it for the subsystems, then you have to calculate it for the total system. So for the subsystem 1, the entropy S1 would be Kb into ln W1. So Kb into ln W1 is 3 into 10 to the power 18. That means it would be Kb into ln 3 plus, you can simply write, we will simply using the what is the properties of log here. So Kb into ln 3 plus 18 into ln 10, which gives us Kb into 1.0986 plus 18 into ln 10 is 2.3025. 42.545 into Kb, which gives us 5.8739 joule per element. Okay, this is the entropy for the subsystem 1. Similar way, for the subsystem 2 also you can calculate entropy S2 equal to Kb into ln 5 into 10 to the power 21. So Kb into ln 5 plus 21 into ln 10. So ln 10 Kb, so ln 5 gives you 1.609 plus 21 into ln 10 is similar 2.302, something like that. Now if you do the calculation, it will gives you 49.96 kV. So this, if you multiply the kV Boltzmann constant with it, it gives you something around 6.89824 into 10 to the power minus 22 joule per Kelvin. Okay. So S1 S2 we got here. Now the last thing is the entropy of the combined system, right? So entropy for the combined system would be S equal to Kb into Ln. So for the combined system, uh, for the combined system W is 1.5 into 10 to the power 40. So let's substitute it here, 1.5 into 10 to the power 40. So Kb would be ln 1.5 plus 40 into ln 10. This further simplifies into Kb into ln 1.5 will gives you 0.4054 plus 40 into 2.30258, which gives us 92.5092 into Kb. That gives us 1.277 into 10 to the minus 21 joule per Kelvin. Okay, this is the S. This is the expression of S. Okay. Okay, so for the combined system, this is the value of entropy I'm getting. Now this same entropy, you can also get the same entropy uh, by in like two different ways you can basically get this expression of the entropy. One is this way, like you um, calculate the multiplicity of the whole system, and from there you can calculate the entropy S1 of the subsystem uh, and the S2 of the second subsystem, and you can just add S equal to S1 plus S2. This also gives you the same result, 1.27 into 22 into 10 to the power minus 21 joule per Kelvin. And also you can do the multiplicity of the combined system W, and from there just substitute that capital W here S into the expression of the entropy, and from there after doing the calculation you will get this whole expression of the entropy. So in both the ways you can calculate the entropy. Okay, so the significance you can write it like this. Entropy is additive. Well, if you simply, that means if you simply add to system, the entropy basically adds up. Okay, so entropy is additive for independent subsystems because of multiplicities. Okay. Okay, so this is a property of entropy you can use. Okay. Okay, so basically if you had multiplicity, and if the multiplicity, like if the subsystem is independent, then you can simply multiply the multiplicities of the configuration, and in terms of entropy you can just add the two different properties. Okay. Anyway, similarly for like this is what I have done for two subsystems. Similarly, if there are like multiple subsystems like 4, 5, 6 subsystems are there. For that case also you can use the similar principle. Okay. So for today's so for today's last section we will discuss about the how will derive the expression of the pressure from this statistical thermodynamics equation. Okay, we will basically like from this expression of the what is this called, this canonical partition function. We will basically write the pressure in terms of this canonical partition function. Okay. So how to do that? So for that we will start from the Helmholtz energy. Okay. So what is the Helmholtz energy? So the Helmholtz energy is the Helmholtz energy is given by U minus Ts. Okay. Where initially A0 is U0. Okay. So you can write this thing like this. So you can write simply write it. So first let me write what we are doing basically first. Expression of pressure in terms of partition function Q. Okay. So first we write the expression of the Helmholtz energy. Now from here you can, if the expression of Helmholtz energy at some temperature is A0 and at that temperature the internal energy is U0, then you can write it like this: A minus A0 is simply U minus U0 minus Ts. So you can write like this. So A minus A0 equal to U minus U0 minus T. S you can write it like this. This is the expression of the S, right? For a canonical system, you can write the expression of the entropy S like this, plus K ln Q. Okay. Okay, so just let me check that. Yeah. So this is the expression of the change in the Helmholtz energy. Okay, now we can further simplify it. So T will cancel. So U minus U0, U minus U0 will cancel. So we'll simply left with KT is a minus and KT ln capital Q, right? This is basically the expression of A minus A0. Now from here what we'll simply do, so okay, so this is basically the change in Helmholtz energy from T equal to 0 to T equal to T, A minus A0 equal to minus KT ln Q. Now from here we will need this expression we'll use. So first let me write why we need this expression of the enthalpy, because simply the fact is we can write the pressure in terms of the Helmholtz energy. Okay, That's why we are connecting to the Helmholtz energy with the pressure to the this canonical partition function. Okay. So let me derive it how this Helmholtz energy is basically related with the pressure. So as you know from thermodynamic potential, that is A equal to U minus Ts, right? Thermodynamic potential Helmholtz energy A is equal to U internal energy minus temperature into entropy. So dA we can write as du minus Tds minus sdt. Now from there dA we can write du as dq minus plus dw minus tds minus sdt. dq you can write is dw. So dq can write is tds, dw can write pdv minus pdv minus tds minus sdt equal to, so TDS will cancel, so dA would be minus pdv minus sdt. Okay, so now from here so P, so you can write this P thing, pressure, so you can write this pressure, okay, as minus of del A by del V at constant temperature, right? From this expression you can write, right, pressure like as a derivative of Helmholtz A with respect to volume at a constant temperature T. Okay, now from here, so entropy is so the Helmholtz energy is related with the uh, partition function capital Q, and pressure is also related with the Helmholtz energy. So that means we can directly connect this partition function Q with the pressure simply. Now, so for that thing, okay, so for that thing you can write, that means P as, so from basically, so let me write from 1 to give some numbers to the equation, so 1 and 2. So from 1 and 2, from 1 and 2 you can write P then as minus, so minus minus, so in the expression of A minus A0 there is also minus, so minus minus will become plus, it will become KT ln Q delta, sorry, delta A, so A is there, so delta of KT ln Q dV of constant temperature, so pressure will be KT into delta of ln Q by delta V of constant temperature. This would be the expression of the pressure, okay, in terms of the canonical partition function. Okay, so this is how we can get the expression of the pressure. Now if we got the expression of the pressure, now we can easily do it for a we can check the expression of the pressure for an ideal monoatomic gas, right? So so for ideal monoatomic gas, you already know, so calculate the pressure for an ideal gas. Okay, so in this case the Q would be simply Q to the power n by n factorial, right? So now if you substitute Q here, so P would become KT into delta of ln Q to the power n by n factorial by delta V, that it is constant temperature. Now next thing is P into KT delta of ln Q n to the power del V at constant temperature plus minus KT would be del ln n factorial del V at constant temperature. Now the next thing would be pressure would be if you do the first derivative here, nkt delta of ln q by del V by temperature at constant temperature, P would be nkt of q delta q by del V at constant temperature. Now in this case, the q, the partition function q would be simply v into lambda q, but v is the volume, so p would be nkt by q delta q by delta v would be q here would be first v by lambda q, delta q v would be 1 by lambda q, so constant temperature, so lambda q will be cancelled, so p will be nkt by v. Nk we already know, nk we can write it as n into na by k, na by r we can write it as na into k, we can write it as r, that is the ideal gas constant, so we can write p equal to n into r, n is mole, into v into r into t. So this is the ideal gas equation, right? So as you can see, this is basically consistent with the thermodynamics. Okay, so using this expression of the entropy, partition function, canonical partition function, with its relation with the pressure, we have substitute the partition for monoatomic gas. We have substitute the canonical partition function, and from there we have also substitute the q value, the molecular partition function for a single molecule, and from there itself we got this we got back basically the expression of pressure, which is nothing but that is coming from basically the ideal gas equation, right? So this is the way that you can use to calculate like the pressure of this. We have this is a very general expression of pressure. Okay, this you can do for any kind of, for non-ideal systems also. Just I am showing you that that is basically consistent of the thermodynamics. So this is it. So so today we have started with the concept of continuing the talk of partition function, canonical partition function, and different quantities like entropy and all. We have done some problems, and from there we have calculated how this entropy is changing with volume and temperature, and at last we have like derived the expression where the partition function is related with the pressure of the system, right? Okay, so that's it for today's class. So let me end the class. So, yeah.